Hi. Okay, so science o'clock. We have a brand new topic today, and the topic is electricity. So you've gone onto a physics topic, and we are looking at something called electric current and charge. So by the end of today, we're going to be able to recall that current is the rate of flow of charge, and we're going to be able to describe the conditions needed for charge to flow. The starter is requiring you to look back to maybe year 8 science, and can you draw an electric circuit? Can you draw an electric circuit using the correct circuit symbols? So I don't want a picture of this, I want the correct circuit symbols. So I want a circuit that has 2 volts, an ammeter, a voltmeter, a battery of cells, and a resistor. If you can draw me a circuit with all those things in correctly positioned, that would be fantastic. Okay, pause and do that. Have you done it? Splendid. Let me just make sure I've got the pen setting on. Pen. Okay, so I'm going to draw. First thing, I'm going to draw the battery because that is a good place to start. And then I'm going to do, go around like this. I'm going to add an ammeter in, across like this, an ammeter. I'm going to do a resistor, which is a rectangle like this. 2 bulbs and a resistor, and I've done 2 resistors. Silly sausage. Okay, I'll draw 2 bulbs. I've done 2 bulbs and 2 resistors. And then the last thing I'm going to add is the voltmeter. You can add the voltmeter anywhere you like, but the most important thing is when you add a voltmeter, you must add it in parallel. So I'm going to add it across this bulb, like this. And that is my voltmeter. That's in red. Okay, tick. Well done, me. Good. Did that what yours look like? Obviously, it can be different. You can have them in a different order. Important things are the lines are straight, like this. Then I have like these right angle turns. They don't have to be right angles, but it's kind of convention. So I haven't put anything on a corner. That makes it difficult to see what's happening. I put them one after the other. The ammeter is in series. And then we've got a couple of resistors and badly drawn bulbs. But the best thing is to perhaps review all of the different components about what they look like and what they are, and the symbol, sorry. What you're going to need, though, is you're going to get a calculator for later on. So if you don't have a calculator, pause and go get your calculator. So let's go. Okay, so first part, I didn't draw a switch in mine. That's what a switch might look like. If you were to take it out of the circuit, it's quite a big switch. But the most important thing is, do you know what the symbol for a switch? I think everyone knows what a symbol for a switch is. So we have a straight line with 2 little circles here and here. And then if the switch is open, which means there is nothing, the circuit isn't working, it's like this. It's like a kind of drawbridge that's been pulled up. And if the switch is closed, the drawbridge is down like this. So the electricity can flow through. We'll come to that a bit more later. So the circuit for a switch, maybe draw that if you didn't remember. Okay, so here we go. Cells. You're thinking, hell, that's not a cell, that's a battery. No, you are wrong. That is a cell, a single one of those. This is a cell. If you want to have more than one joined together, then it becomes a battery, giving its full name a battery of cells. So that is just a cell, and that is the correct symbol for a cell. We have our circuit. So this is the normal circuit, and then we have a longer line and a shorter line carrying on. When you see them printed, the shorter line is normally thicker, but when you're drawing it by hand, it doesn't really matter so much. So that is a cell. A battery, for example, is more than one cell. Here we go. I just said that a moment ago. So this is a car battery, but you can have multiple cells joined together. So a battery is when you join cells together in a loop, not in a loop, in a sequence. You can draw, if you just have 2, you could draw like this. So that is an example of 2 cells to make a battery. If you have more than 2 or multiple, you could do this little dotted line, which just doesn't tell you how many there is. It just says there are multiple cells joined together. A bulb, this is an old style bulb. This is a filament bulb. They don't really do those many more. This is a kind of example of a filament bulb, but a general circuit for a lamp is this. A circle with a cross right in the middle. Nice. You knew that. These are resistors. Resistors we'll do in another couple of lessons in more detail what they do, but basically their job is to resist the electricity flowing through the circuit. They are called resistors. This one is really small. Actual size is, it's, I don't know, it'll be like the width of a fingernail. You know, they're not very big. It's pretty small. Actually, if you have one of those pencils where the rubber, this one's used up, or been eaten by the dog. But if that comes out, that's probably a good size for what a resistor might look like, one of those resistors. This one's a variable resistor called a rheostat. That's pretty big. That's like the size of 2 cans of beans put together. Full-size cans of beans, not small ones. And the symbol for these are, a fixed resistor is a rectangle joined at either end, and a variable resistor is exactly the same, but then they've added an arrow going through at 45 degrees. So if you didn't know that, make sure you draw those down. Okay, splendid. Measuring instruments, meters, ammeters, and voltmeters. So in school, we have these kind. They're not exactly this type, but we have digital voltmeters and digital ammeters. You plug them in, and it has a little kind of display, like a calculator display. It's called a liquid crystal display, and that tells you the value. Other versions are these ones. These are needle displays. What's the proper name? Moving dial? I can't remember. Yeah. And what happens is when the current goes through, the needle kind of goes up. You see that like in a car. If you're driving a car, the speedometer will change around like that, or the fuel gauge. That's how that one will vary. So an ammeter is an A in a circle, capital A, and a voltmeter, as you might have guessed it, is a V in a circle. Okay? Did you get that? I'm down. If not, don't worry. Aha. Now, I know, because I did this lesson only a day or two ago. What are the properties of metals that you know or can think of? Think, pair, share. Obviously, you're in lockdown, probably at home by yourself. So imagine, talk to something, a calculator, phone a friend. What properties of metals you know? That you did this last week, a couple of lessons ago. So, yeah, do that. What have we got? Hopefully, one of the things you've got is that metals are good conductors of electricity and heat. Electricity is all that matters today. Why are they good conductors? Again, the other day we did a lesson on this, which was metallic bonding and the property of metals. Metallic bonding and the property of metals. If you remember, metals are arranged in a kind of lattice. So the atoms are arranged in nice regular rows, slightly offset from each other. And then in between those, we have that sea of free electrons, delocalized electrons that can travel around. So that's why they're good conductors of heat, and that's why they're good conductors of electricity, because they have those free delocalized electrons. And those electrons delocalized means they can move. That's why they are such a great conductor of electricity. What do we know about electrons? They're small. We know that they have almost a mass, but we also know that they have a charge. What's their charge? Negative charge. Well done. And so if those electrons move through the wire as an electric current, they are flowing. And that's the definition of what an electric current is. It is the flow of charge. Nice and simple. A little definition for you to write down. Electric current is a flow of charge. So if these electrons can move through a wire, therefore there is an electric current. It doesn't have to be electrons. You can have currents in things that has like ions can work, and other charged particles can work. So if you have moving charged particles, that's a current. But mostly, and for this course, it's going to be electrons. Okay? And here's an equation. First equation in this topic, and we use the letters Q to describe charge. Why do you use Q? I don't know. There's only 26 letters in the alphabet. There are more variables and things that we can describe. Also, if you use C for charge, C means something else, and C is the unit for charge that it's measured in. So charge is Q, the letter Q. Current is I, because it used to be intensity in French, I believe. And time is T, lowercase t, very important. Not capital T. Capital T means temperature. And the equation is Q equals IT. Q is equal, that's the worst equal to I times T. Q is I times T. So charge in coulombs is equal to current in amps multiplied by time in seconds. Can you put that into a triangle? A formula triangle, like this. What goes at the top? What goes at the bottom? Go on, pause, do that. Should only take you a second. Okay, let's see what you did. Did you do this? If you did, well done. If you didn't, it's okay. Try again, or at least copy this. So, what do you need to have electric current flow? And what are the most basic requirements for this to happen? Now I'm going to see if I can exit this PowerPoint, discard, and I will jump to this. This is a website called PHET, P-H-E-T, and I'll be using it a lot, and it's brilliant for so many different physics topics. And here we have a simple circuit, but we notice these little negative things, these are electrons, they are not flowing. What do we need to have the current or the electrons to flow in this circuit? Well, hopefully you've noticed that the battery, the cell, is not attached. I've attached it. Something's still missing. What is missing? Why isn't it flowing? There we go. It wasn't flowing because there wasn't a proper loop. There wasn't a complete loop in the circuit. So it only works if you have something to push the electrons around, a battery, a cell, and the circuit has to be complete. There are probably other things you can do to break a circuit, but those are the two basic fundamentals. Is the circuit a complete loop? And does it have a power supply? Does it have a source of energy to push those electrons, the push to help the electron flow? And here we are, here are the electrons flowing around the circuit. Nice and simple. I can switch it to the circuit symbol view. Here we go, here's the cell. That doesn't change. There we go. So let's go back to this PowerPoint. Okay, what do you need to have the circuit flow? You need a push, which is cell, battery, and you need a complete loop. If it can't flow all the way around, it won't work at all. Let's the equation again. Here's a little fun fact. If you're measuring, Q equals IT, rearranged like this, I is Q over T. If you have 1 amp, that is 6.25 quadrillion electrons. So that's 6.25 times 10 to the 18 electrons, which is quite a lot. I'm going to change this to a red pen. You can't see that otherwise. 6.25 quadrillion electrons. That's quite a lot. So 1 amp has a lot of electrons. Okay, so here we have. Let's put the triangle back on the top for you. Yeah, red pen. Sweet. IT. It tells me a current of 12 amps. Current I is 12. Passes through a kettle for 20 seconds. T is 20. How much charge has flowed through? Flowed through. So the equation should be this, I times T. 12 times 20. I think I did that already. Yeah, I did. So 12 times 20 is 240 coulombs. Nice. Did you get that? Good. Right, next one. We have a current of 200. I is 200. And time is 10. Right, careful. I'm not trying to catch you out. 10 is in minutes. And we need it in seconds. So actually it's 10 times 60. 600. That's not 600. 600. And again, it's the same two, I and T. So let's multiply them together. Is 120,000 coulombs. And the last one, I'm not even going to break it down for you. A charge of 200 flows through an iron for 10 seconds. What is a current? Okay, this one's different though. This one's given us charge. So Q is 200. The time is 10. So it's divided. Oh, that's badly positioned. 200 divided by 10 is 20 amps. That's a lot of current. 20 amps is bad. If there's 20 amps going through your house, you should be aware. Did I just make that up? Okay, so time for you to have a go. Pause. Answer those two questions. Calculate the current that would need to flow for a charge of 1,000 coulombs in 10 seconds. Calculate the time a current of 1 milli, ooh, tricky, milli would need to flow so 1 coulomb of charge is flowed. Pause, ask the questions. You done? Good. Right, so let me put the equation back up. Q, I, T. So what did you do first? If you were sensible, the first thing you would have done is you would have written down what you know. So for question 1, we have Q. Q is 1,000. C. And we know T is 10. So we just do 1,000 divided by 10, which is 100 amps. The next one is trickier because it's giving you in prefix, so it's standard form. So again, you write down what you know. So I'll do it over here. I is 1 milliamp, which is the same as 1 times 10 to the minus 3 amps. And Q is 1. That is 1. So it wants to know a time. So time is 1. How can I not do a 1? 1 divided by 1 times 10 to the minus 3, which is a bit trickier. So you put in your calculator. Do you know how to do standard form in calculator? Your calculator should have this button here, EXP. Okay, so 1 divided by 1 EXP minus 3, and that gives you 1,000 seconds. Cool. Next one. Okay. New thing. Name the unit of charge and write its symbol. Name the unit of current and write its symbol. In the equation, current, charge times current times time, what unit should be used for time? Actually, something's gone wrong there. That should be charge is equal. My apologies. Current times time, what unit should be used for time? And calculate the amount of charge that passes through a cell when a steady current of 0.5 amps flows through these times. Can you do it without a calculator? Check it out. Right, pause. Next set of questions. Have you done it? Good. Now, hopefully you've done it, not like waiting for me to give you the answers, because you won't learn in that way. So do it. Get it wrong. Here's a great opportunity to get it wrong when you're home. No one can see you make a mistake. The name for the unit of charge is measured in coulombs. And it's measured in C. Name for the unit of current is amps, and it's A. Time, in this equation, what should be the unit of time? Time is seconds. We do small s. And here we have, calculate the amount of charge that passes through a cell when a steady current of 0.5 flows through these times. Okay, so it's just as simple of, remember, Q, I, T. So they give us the same current each time, 0.5. The The time is the only thing that changes. So the first one is 0.5 times 20, which is 10. The second one is 0.5 times, now this one is 5 times 60. So that's the same as 0.5 times, I can't do 5 times 60, 300, which is 150. And the last one is 0.5 times 1 hour. But we need to do how many seconds are in the hour. So 1.5 times 2,600, which I'll do for you to do. Okay? This is a thinking thing. Okay? So, the wheel on an upside down bicycle is useful for a model of a current in a series circuit. The little dots can be painted around the edge of the wheel to represent electrons. If you push the wheel at one place, the whole wheel turns as soon as you start. What does this suggest about the movement of electrons in a circuit when the current flows? It might be easier if I jump back to this little animation. Where was the animation? So here we go. Put it back to the battery. Look at those electrons. Look at the electron here. These electrons, pick any electron. Okay, look at them. And then look at all the other electrons around that circuit. What do we notice? They're all moving. So you can't have one move and not move. So they all have to be moving at the same time. And then look at their speed. Look at how fast they're moving. They're all moving at exactly the same speed. And it's kind of like it's like a strange cube because the whole thing's going around in a loop. You can't have one electron going really fast because they would catch up with the electron in front and that one would block the way. And you can't also have another electron going really slowly because they would block the electrons behind. So in a circuit, in a series circuit like this, all the electrons have to travel at exactly the same speed. Like if there's one slow electron, then they all have to travel as slow as the slow electron. So in a series circuit, they're all traveling, they have to all travel, and they all travel at the same speed. So wherever you look in the circuit, you'll see the same amount of electrons passing by, which means, let's see if I can do this, I can add another ammeter. Wherever I look in the circuit, the current should be exactly the same. There we go, 0.9 there, 0.9 there. Because the current is just how many electrons pass every second. If it's the same, it's the same. So everywhere in a series circuit, the electrons are the same. Let's go back to this one. Excuse me, hiccups. In a real circuit, what gives push to the electrons? Hopefully you just saw that from the little animation. What was pushing the electrons? That is the cell or the battery. When some electrons in a wire are pushed along, the electrons in front of them move as well. Explain why. Well, as I just explained, as I just demonstrated, you can't have one electron move and the other one's not, because they would block it, because it's a loop. Okay, so if one moves, they all have to move. They all have to move, and they can all move. It's like when you were in school and everyone's going up the stairs. If someone goes really slowly, the whole set of people moving up the stairs moves really slowly. If someone stops, everyone on the stairs has to stop because you can't get past. And the same with the electrons in the wire. They all have to move at the same speed for it to flow. When you switch on a switch which contains bulbs, all of the bulb's lights strike away. Try and use the model to explain why this is. And I suppose that's kind of like when you're all like queuing to go in somewhere, there's a big queue, and that no one's moving. And then if you open the door at the front, the person at the front goes through, but as soon as the queue starts moving, everyone can move at the same time because you've got people in your queue, okay? And as soon as the first person in the queue starts moving, there's space for the next person, then the next person, then the next person. So that's why when you flick a switch, all the electrons start moving because the one at the front can move, so then the number 2 can move, and then the number 3 can move, and they can all move along the circuit. So that's really important. There's one more thing that I think I forgot to add. I'm going to go back to the little animation, and here we go. I face is in the way, that's a problem. I hate it when my face gets in the way. So here we go. Let's look. Here we have the electrons traveling around the circuit. The electrons are traveling around the circuit. We can see that. This is classed as the electron flow. And if I do it like this, so that end is your, that is the positive end of your battery, yeah? That has a little nipple sticking out the end. Okay, that is the positive end on the battery. If you draw it as a circuit diagram, the positive end is actually here, the long bit. The long part is the positive end of the battery. And we know that electrons are negative. And so when you're having electrons travel around the circuit, they're negative. So they have to come out the negative end, normally, come out the negative end, and they travel around the circuit, and they're attracted to the positive end. So we know electrons are negative, so they will be attracted to the positive end. Now, unfortunately, electricity was discovered before they knew about the electron. And when they were talking about electricity, they always talked about it going, they didn't necessarily know what was happening inside the battery or the cell. They just knew this electric current was flowing. So they always decided that electricity went from positive to negative. So when you're talking about electric current, you're actually talking about it wrong. It's wrong. Now, when they discovered the electron, they took a while maybe to realize what this is, and they should have changed, but they didn't. They didn't want to change. They refused to change. So instead, they're just wrong, and they have two ways of describing it. So actually, when you're looking at electric current, when you're talking about current, sometimes called conventional current, it actually goes from positive to negative. Now, you know that can't be true, because you know electrons are negative. Why would a negative electron go to the negative end of a battery? What do we know about those like charges? They repel. So the electron's not going to go to the negative end because it will be repelled away from that negative end. So that's wrong. So actually, the direction of current flow is wrong. It goes from positive to negative. It's wrong, but they still talk about it. And in most questions, they'll talk about what's the direction of current. Then you have to talk about it wrong. If they ask about what is the direction of electron or charge flow, that's correct. Crazy, I know. So let's just do a little diagram to finish this off. So if you have, here is my cell, and here's my battery. Now remember, the long end was a positive. So if my battery was like that, that's how it would look. Quality battery drawing, I've got to say. So if that's positive and that's negative, the electric current comes out of the positive and into the negative. I should have chosen a different colour for that. Do that in green. Current goes out of the positive. So current, brackets conventional, goes from positive to negative, and is technically wrong, but no, they always use it. What colour should we do for this? Yeah, yellow should work. This is charge or electron flow, and that one goes from negative to positive. And that one is right, but unfortunately, they talk about current and they talk about electron flow in the wrong way, even though in reality they are describing the same thing. So the direction of electric current and the direction of the electrons, when we're talking about circuit, go in the opposite direction. I think I'll review that again because it's a bit crazy next time. But don't forget to answer the questions and don't forget to send your work to your teachers. Okay, thank you. Love you. Bye.